Hello everyone, my name is Chen Dingyi. Today I'm happy to share something from mathematical analysis with you. My topic is exterior points, boundary points, and geometric examples. In this video, we will look at how points divide a mathematical space into different parts. Let's start. Let's start with the basic idea. Imagine we have a universal space. We call the space Rn, which is just a normal Euclidean space. Inside the space, we pick a set, and we call it S. Every single point in this entire space can be put into one of three groups. We use neighborhoods to decide where a point belongs, which you can think of as small circles around the point. These three types of points are interior point, exterior point, and boundary point. Together, these three groups divide a whole space perfectly. Now let's look at what each term means. First, what is an interior point? Look at figure 1. We say a point X is an interior point of S if we can draw a small ball around it, and that ball stays completely inside the set S. If we collect all these interior points together, we call it the interior of S, or init S. To understand this better, we use the word neighborhood, as you can see in figure 2. A neighborhood of X is just an overset that contains X. If a set is a neighborhood of a point, it means that point has enough space around it to stay inside the set. Next, let's look at the exterior points and boundary points. Look at the figure 3. An exterior point is the opposite of an interior point. A point is an exterior point if we can draw a small ball around it and that the ball is completely outside the set S. This means the ball is inside the complement of S. We call this connection of these points the exterior of S, or exterior S. Next, let's look at the boundary points. Let's look at the figure 4. What if a point is right on the edge? We call this a boundary point. For a boundary point, no matter how small you make the ball around it, this ball will always touch two things. It will touch the inside of S, and it will also touch the outside of S. This connection of these edge points is called the boundary of S. Now let's talk about the main theorem of this project. This theorem gives us 4 important properties for any subset S. A is exterior S equals to interior Rn except of S. Boundary S equals to boundary Rn except of S. And interior S, exterior S, and boundary X are mutually disjoint sets, which means they have no overlap. And then we can say Rn equals to interior S unit exterior S unit boundary S. Let's prove it. First, we prove A and B. It is clear directly from the formal definition of exterior and boundary points. We know that init S is inside S and exterior S equals to init R except of S, also inside R except of S. Since the set S and its complements are disjoint, it immediately follows that init S intercept exterior S equals to empty set. And then let X inside boundary S. By definition of boundary point, we know that it means there exists for any R larger than 0, ball XR unit S is not empty, which equals to for all R bigger than N0, ball XR is not inside Rn except of S. By De Morgan's law, we can say X is not inside exterior S. So we know boundary X intercept exterior X is also empty. Symmetrically, by replacing S with Rn except of S, which is the complement of S, we obtain X not inside init S. Thus, boundary S intercept init S is also empty. Now let's prove the D. We only need to show Rn is inside init S, unit exterior S, unit boundary S. Let X inside Rn. We give two cases. The case one is X is inside init S and exterior S. Then obviously X will inside initial S in unit exterior S, unit boundary S. In case 2, X is not inside interior S and X also not inside exterior S. By the same way, X not inside interior S, we can rewrite it as for any R larger than 0, ball XR is not inside S, which means for any R larger than 0, BXR intersect Rn except of S is not empty. Similarly, since X is not inside exterior S, where exterior S equals to interior of Rn except of S, we have X not inside exterior S is equal to for any R larger than N, 0, ball XR intersect S is not empty. Therefore, we can say X is inside boundary of S, which is also inside interior S, unit exterior X, and unit boundary S. So finally, we prove that Rn is equal to the collection of interior S and exterior S and boundary X. And they don't have any overlaps. Now let's see these pictures. In this page, we can see this very clear. We take a ball as an example. The first picture shows the interior. It is the safe inside area. And for the boundary, it is the yellow line on the edge, which is the edge of the ball. And also for the exterior, it is the space of outside of the ball. We can see the space Rn is partitioned into distinct sets, interior, boundary, and exterior of S. In conclusion, we have shown that any mathematical space can be cut into 3 clean, separate pieces: the interior, the boundary, and the exterior. No point can belong to two pieces at the same time, and no point is left out. This simple idea of partitions in a space forms the strong foundation for advanced mathematics, like studying limits and continuity. Thank you very much for your time and listening. I'm happy to take any question you may have. Thank you.